Imagine a planet so strange, so physically impossible, that the very force holding the universe together, gravity, seems to stop working the way it should. A world where mountains rise higher than physics allows, where clouds drift upward instead of sinking, where objects would fall so slowly you could follow them with your eyes. And yet this is not a theoretical exercise or a science fiction fantasy. This is a real discovery, a real exoplanet now baffling scientists using NASA's most advanced observatories. When the James Webb Space Telescope first measured its density, the numbers didn't just surprise scientists, they stunned them. The planet was far too large and far too light. In fact, it behaves as though it has almost no gravity at all. How can a world the size of Jupiter be as fluffy as a cloud? How can something with so much volume have so little mass? And why does its atmosphere stretch outward like a balloon inflating into the void? These are the questions researchers now face as one of the strangest planets ever detected forces us to rethink everything we know about planetary formation. At first glance, this world looks like a typical gas giant, massive, bright, wrapped in thick layers of atmosphere. But Webb's measurements revealed the truth. It is one of the lowest density planets ever found. Its density is so small that if you could place this planet in a giant cosmic ocean, it would float. Even Jupiter doesn't come close to this level of puffiness. According to our physics, gravity should pull the atmosphere inward, tightening it, compressing it, making the planet smaller and denser. But here, the opposite is happening. The atmosphere is so extended, so inflated, that the planet looks like a translucent sphere wrapped in haze. And when astronomers tried to simulate this planet using conventional models, the simulations failed. Nothing matched what Webb was seeing. So how does a planet defy gravity? How does a world become large without becoming heavy? And could this bizarre object reveal something new about how planets are born, or even how gravity behaves in extreme conditions? To understand the puzzle, scientists began to search for clues within the atmosphere itself. That is where the mystery deepened. Astronomers first suspected heat. Many superpuff planets orbit close to their stars, and the intense stellar radiation heats their atmospheres, causing them to expand. But when researchers measured this planet's orbital distance and temperature, they realized the heat wasn't nearly enough to explain such extreme inflation. Even the hottest known gas giants don't become this puffy. Something else had to be happening. The next explanation was composition. Maybe the planet was made almost entirely of hydrogen, an extremely light element that expands more than others. But even a pure hydrogen planet shouldn't become so oversized. The numbers still didn't match. Then came the age hypothesis. Perhaps the planet is extremely young, still in the process of cooling and shrinking. Young planets can appear large at first, but this world orbits an old star, ancient enough that the planet should have compacted billions of years ago. Everything pointed to one conclusion. This planet was breaking the rules. The next step was to look deeper, literally. Webb analyzed the atmosphere using infrared spectroscopy, hoping to detect fingerprints of water vapor, methane, carbon dioxide, or other molecules. But instead of detailed signatures, Webb saw something paradoxical. Almost nothing. A smooth, flat spectrum. As if the atmosphere were hidden behind an enormous veil of haze. But this haze wasn't ordinary. It would need to be thicker than anything in our solar system, thicker than Titan's orange smog, denser than Venus's sulfuric acid clouds, and not just thick, but consistent enough to hide nearly all chemical features from one of the most sensitive telescopes ever built. If that haze were real, it meant the upper atmosphere was so inflated, so extraordinarily extended, that Webb was only seeing its highest layers. The planet beneath could be much smaller, but hidden entirely. Yet even with this explanation, one problem remained. How does such a gigantic haze layer stay stable for billions of years? That's when another theory emerged. Maybe the planet is continuously replenishing its atmosphere from the inside. If internal heat, geological activity, or tidal forces are injecting gas upward, the atmosphere could remain inflated indefinitely. But this demands a source of energy we cannot see, something buried deep within the planet. Could this world be heated from the inside? Could an unseen companion be stretching it gravitationally? Or, most intriguingly, could there be an unknown process happening within its core?
To explore these possibilities, scientists ran high-resolution simulations of atmospheric escape. If the planet's gravity is too weak to hold its atmosphere tightly, then hydrogen and helium should drift into space continuously. And perhaps that's exactly what's happening. The planet may be slowly evaporating, peeling like a cosmic onion. Webb detected faint hints of atmospheric escape, gas drifting away in thin streams. But again, not enough to explain the extreme puffiness. Something was maintaining the inflation. So researchers considered the tidal heating hypothesis. If a hidden planet nearby is tugging on this world, stretching and compressing it, internal friction could create heat, similar to Jupiter's moon Io, the most volcanically active world in the solar system. But when astronomers examined the system, they found no massive neighbors close enough to generate such forces. No orbital distortions, no gravitational fingerprints. The system looked quiet. Too quiet. And yet, the planet's atmosphere behaved like something was constantly stirring it from within. Could this world possess a deep internal ocean of volatile ices boiling upward? Some models propose that cryovolcanism eruptions, like those on Neptune's moon Triton, could eject massive amounts of gas into the atmosphere, maintaining the planet's inflated size. But to achieve these effects, the cryovolcanism would need to be unlike anything we've ever observed, continuous, powerful, and on a planetary scale. Then came the most radical idea. The planet might be mostly empty space, a hollow core structure. Not literally hollow, but composed of extremely low-density materials, perhaps trapped heat, exotic phases of hydrogen, or a partially collapsed interior that never fully condensed. While exotic, this idea fits one key observation. The planet is large, but extremely light. And if the core is unusual, then gravity throughout the planet would be weaker than expected, creating the slow-motion atmospheric behavior we observe. But even this explanation leaves scientists with unanswered questions. Why would a planet form this way? What prevents it from collapsing under its own weight? And how has it survived billions of years without shrinking? Every model fails somewhere. Every explanation adds new mysteries. And that's why this planet is so exciting. It's not just an odd world, it may represent a whole new class of objects we've never understood.
What happens next will determine whether this discovery becomes just a cosmic curiosity or a revolution in planetary science. NASA and ESA have already scheduled deeper Webb observations targeting infrared wavelengths sensitive to exotic aerosols, escaping gases, and hidden heat sources. If the haze theory is correct, Webb should detect subtle scattering patterns, signatures of tiny particles suspended high above the planet. If atmospheric escape is extreme, we may see ultraviolet evidence of hydrogen streaming into space, creating comet-like tails. If internal heating is real, Webb may detect hotspots or thermal anomalies, revealing a dynamic core. And if tidal forces are involved, the planet's orbit may show subtle inconsistencies. But here is the most intriguing possibility. This planet might challenge our assumptions about gravity in extreme environments, not by changing the laws of physics, but by pushing them to their limits. Low density, exotic atmospheric chemistry, internal heating, escape mechanisms, haze layers, each by itself is unusual but possible. But all of them at once? That's unprecedented. And it suggests that planets can evolve in ways our current models do not capture. If more worlds like this exist, our understanding of planetary formation, migration, and atmospheric stability may need a complete overhaul. We may discover that gas giants can form inflated phases lasting billions of years, that atmospheric chemistry can create long-lived haze structures, or that internal processes can counteract gravity far more effectively than we ever imagined. Whatever the answer is, one thing is certain: this planet is forcing scientists to rethink fundamental ideas. It is a reminder that the universe is still full of surprises, full of worlds that don't simply challenge our expectations, but break them completely. And as Webb continues scanning the galaxy with unprecedented precision, we may soon find that planets like this are not the exception, but the beginning of a much stranger cosmic story. The planet that defies gravity isn't just puzzling. It's a sign that the universe still has secrets left to reveal. And this is only the first chapter.